All right, our next topic is a slight detour. So we're gonna use these kind of tools to prove the absorption of Bella-Boulouvas's two families theorem. And the tool that we're gonna need is wedge product of vectors. So we will start with the easier ones, the second exterior power. Okay, so let's start with the vector space. Let V be a vector space over some field F. And let's say V1, V2, Vn be a basis of V. So just to simplify, so we have a finite dimensional vector space. And for a given vector space, V, we define the dual space. The dual space V star, denoted by V star, as the vector space consisting of all linear functions from V to F. Okay, so that's a dual space. And then it's easy to observe the following, that the dimension of the dual space is equal to dimension of the original vector space. Why? Because these are linear functions, right? So for each basis element, if you decide the first element goes to some number, second element goes to some number, third element goes to some number, that determines the function completely. So the dimension of V star is at most the dimension of V, right? It only depends on this dimension many elements. And moreover, you have a function giving 1, 0, 0, 0, right? So for the first element of basis, you give 1 and all others you give 0. Or you could give a second element to be 1 and all others 0, or third element 1, all others 0, and these vectors are linearly independent. So, and they span everything. So that's why we have a same dimension. So the vector space and its dual space have the same dimension. Now, eventually, we're going to define KAIST exterior power, but in order to have a concrete idea, we will start with the second exterior power. So let me start with the alternating bilinear forms. On alternating bilinear form on V over F is a function B from V times V to F satisfying three properties. So the first property is when you put 0, when you put the same thing, then it's 0. Second property is when you put U and V, and when you swap the order, then you get the negative sign. And so third property is linear. So C1, U1 plus C2, U2, and V is a linear combination of U1, V plus. So some of you may say that, oh, why do we need the second condition? I mean, first condition. You can think that second condition implies the first condition, right? When you say U and V are same, then X is like B of V is equal to minus B of V, so twice B of V is 0, so B of V is 0. Yeah, so in general, in most of the cases that's true, but we may work on the field of order 2, so 1 plus 1 could be 0. Okay, so That's why we will just list them as a separate condition. And then the second exterior power of phi denoted by this is the dual space of the vector space of all bilinear or alternating bilinear forms on V over F. Okay, so that's the definition of the second exterior power of the vector space. All right, so we need the convenient notations, right? We need some notation. So, right. So for an alternating bilinear form B from V times V to F, and U and V in two vectors, we define U wedge V as so this is an element of the dual space of the vector space of alternating bilinear forms. That means it maps a linear function, right? Whenever I give it an alternating bilinear form, it has to give some number, something in F, right? So U wedge V and B is gonna be B U V. That's the definitions, right? So whenever I give an element in this vector space of alternating bilinear form, then it assigns some number in F, right? So B U V is in F. So this is the definition of U wedge V. All right. Now I'm going to tell you properties. What are the properties? So here's the lemma. So if okay, so I have already assumed the basis. So Vi wedge Vj, where I is less than j is less than n, is a basis of wedge product. Second is a basis of the second exterior power of V. So why? Why is this the case? So first of all, I need to prove that anything, any vector in this dual vector space is spanned by the basis, and also it's better to show some basis, right? So I'm going to show you a basis. So for all ij, let eij be the elements of the second exterior power such that yes, eij is the right. Yeah, so how do I do that? Well, if a no no, first of all, let me make the bilinear forms. Yeah, for A, which is A1 up to AN in F to the N, and B is B1 up to Bn in F to the N. Oh no, it's a linear combination, sorry. Yeah, so A is a linear combination of AI VI, and B is a linear combination of BI and VI from 1 up to N, 1 up to N. We define an alternating bilinear form Eij as a function, right? Eij AB to be AI Bj minus Aj Bi, okay? So that's in F. So this is, now you can easily check that this is a bilinear form. If you put the same vector twice, then it will give me 0. If you change A and B, if you swap A and B, then you get the minus sign. And any linear combination will expand. So this is an alternating bilinear form. All right? Now, so these are bilinear forms. And now, what do we do? So Eij, if I put Vi and Vj, that's gonna be a right. So this is 1 if I is less than j, minus 1 if I is bigger than j, and 0 if I is equal to j, right? All right, so now let Vi, let's look at this. I first claim that these things are linearly independent. Why? Because if they are not linearly independent, then I have something like this, right? There's some linear combination which add up to 0, but then Cij.
우선 아이폰을 잠금 해제하셔야 합니다.
Vj, and then I put Eij, Ei prime and J prime. So what? So this is 0, but this end up being what? What do you get? This is same as saying Cij and Ei prime, J prime, and Vi, Vj.
알겠습니다. 웹에서 시작.
Right? And now notice that if I prime J prime is different from Ij, then this is 0. So the only place it could be non-zero is when Ij are equal. So I prime J prime. Right? So actually I don't need to, yeah, so okay, let me fix I prime J prime, then it's 1 if yeah, right, if I is equal to I prime and J is equal to J prime and 0 otherwise. Right? I am assuming that I is less than J, I prime is less than J prime. So this is Ci prime. So that means all the coefficients are 0. The second claim is they are linearly independent. Oh no, they span everything. How do I know that they span everything? Well, actually, the space of all alternating bilinear form is same as the space of skew symmetric matrices. Right, skew symmetric n by n matrices, and the dimension of this is what? And choose 2, right? Because you have a matrix and diagonals are 0, and below is the negation of the upper triangle part, and this is 1, 2, 3, 4 up to n minus 1. So you add all these numbers, you get n choose 2, right? So dimension is most n choose 2, and we have a linearly independent vectors. So that means this means that vi wedge vj is a basis of the second exterior power of v. Okay. Did I cheat? No, I don't think I cheated. But dimension of dual space is right. So I mean the reason is this space has dimension n choose 2. So therefore the dual space also has dimension n choose 2, and we have n choose 2 vectors which are bases. Now let me tell you quickly about the easy properties. So for instance, v is 0. Why? Well, we can use simple properties, like for instance ci vi wedge di vi, and then you have a the only thing that survive. Oh yes, the same thing, ci. Then when you expand cj vj, so when you expand it's ij I less than equal to j, it's gonna be like ci vi wedge vj minus ci vi wedge v plus ci vj wedge vi plus ci vi wedge vi, but this is 0 and these two cancel each other, right? And v wedge u is minus u wedge v. That's easy. Well, why? Well, the thing is, if I have a bilinear form b, then this is b v u, and that's minus b u v. That's equal to minus u wedge v and b, right? And another easy thing is when you have a linear combination, then this is equal to u1 wedge v plus c2 u2 wedge v, right? And again, this is easy, so because c1 u1 plus c2 u2 wedge v, and then when you assign b, it's gonna be like a b and c1 u1 plus c2 u2 and v. And when you can expand, right? And then c1 u1 wedge v b plus c2 u2 wedge v b, and that's a c1 u1 wedge v plus c2 u2 wedge v b. All right, so all these things are natural. And last property, uv is 0 if and only if uvr is linearly dependent right? So for instance, this direction, if they are dependent, then u is k times v, right? So then it's easy. What about the forward direction? If u, v are independent, then we can extend. Then we can extend to a basis, right? So then u wedge v is non-zero. All right. So all these things are the simple properties of wedge product. And later in the next video, we'll talk about the KAIST exterior power, and the same rules for manipulating wedge product will work. All right. So that's it. That's it for this video.